There is a factory and it has n machines in it. And these machines can be used to make products. Our goal is to make T products. And for all these machines, we know the number of seconds it needs to make a single product. Also, these machines can simultaneously run. We need to find what is the shortest time needed to make T products. So we have number of products as 3 as an example, and we have the number of products as 7. So we have to make 7 products from these 3 machines. Also, we are given with number of seconds each machine takes to make a single product. So the first machine takes 3 seconds to make or deliver a single product. The second machine takes 2 seconds to deliver a product, and the last one takes 5 seconds to deliver a product. So we need to tell what is the shortest time we can deliver the given products. So let's write all these information, and from here let's try to make or build the intuition behind it. So 3 machines, 3, 2, 5 is the times given, and we need to make total 7 products. And these machines can run simultaneously. This is the first key thing to note. So if I write one statement at any given point of time, can we tell the total number of products machines can make? This would be our first question. Can we do this? So let's try to see if we can do this. So take t as 5. So at t equal to 5, please tell me the total number of products your machine can deliver. So if we look at the first machine, it takes 3 seconds to deliver, and we have 5 seconds. 5 divided by 3 is, we can tell the product, right? If I have to go even basics, then 3 seconds, I have just added the unit of time as seconds. You can take any unit of time. So 3 seconds it takes to make one product. In 5 seconds, how many products it can make? So it can make 5 divided by 3. So this would be 1. Similarly goes for second machine, which takes 2 seconds. So 5 divided by 2. So this would be 2. And for the last machine, 5 divided by 5, it will be 1. And for this was 5 by 3. So if we add all these, so we get 4. So at t equal to 5, we can make 4 products. So it's simple, right? At any given time, if we can calculate the number of products, then we can surely calculate when we can hit 7, because we need to hit 7 and we are at 4, number 4. So we must increase time, right? So in other words, if I have to, then I can say that for t equal to this, we can iterate over this list, right? Like we were calculating for each machine. In the question, I think constraint is 10 to the power 9. For these seconds, we need to iterate for each individual machine, and that too is 10 to the power 9. So clearly, we need 2 loops, right? First loop to calculate the time, since we need to hit 1, 2, 3, 4, 5, 6, 7, and then for second loop to calculate these seconds. That was for, let's say, for 5, we are calculating for first machine 5 by 3. Then we iterate for 5 by 2. Like in this second loop is for iterating over here. That means total we will require n square. That is 10 to the power 9 square. That is 10 to the power 18. And in 1 second, we know this, in 1 second we can go up to at most 10 to the power 8 operation. And this is 10 to the power 8 or 7, whichever you can, but this is 10 to the power 18. So n square algorithm won't work. So this algorithm is correct, but it won't work. We need to bring down the time complexity such that it should work. Let's see more. We have again 3 machines, and the number of products is 7, and these are the time taken, 3 to 5. Let's try to plot time versus number of product. So at 0 second, how many products you can make? Of course, you will have 0 products. Then at time equal to 1, how many products you can make? We require minimum 2 seconds to make one product. So at time equal to 1 second, we have 0 products with us. Then at t equal to 2, how many products you can make? You can make only 1 product. Then at time equal to 3, how many products you can make? So at t equal to 3, that means this machine can make 1 product, this machine will make 1 product. So in total, we can make 2 products, right? So at time equal to 3, we can make 2 products. Then at t equal to 4, how many products you can make? At t equal to 4, the second machine can make 2 products, and the first machine can make 1 product. So that means we can make 3 products. Similarly goes for 5, we can make 4 products. Then for 6, we can make 6 products, right? The first machine will make 2 products, then the second one will make 3 products. So 2, 3, and 5 is 1. So this is 6. Okay. Then at t equal to 7, again we can make 6 products, and then t equal to 8, we can make 7 products, and then t equal to 9, we can make 9 products, and this goes on. But if we look into this, we need to make 7 products, and at t equal to 8, we have 7 products. And then if you try to look further, then of course you will get more than 8 products, right? Because as the time increases, delivery will also increase, right? Because we can clearly see the trend of the graph. This, we need to give the minimum time required, so that is 8. 8 is our answer. 9 won't be the answer because that is not minimum, even though we can make, but that's not minimum. And if you look over this side, then you won't have any answer. So this is like a waste to watch this even, right? But what we were doing earlier in previous algorithm, we were running over here also. This was all waste, right? The second key observation is, since the graph is increasing, then we can say it is a monotonically increasing function. Hence, earlier we were trying to build the logic over linear search, right? We were linearly searching. But if we say this is monotonically increasing function, therefore we can apply binary search over here, right? And that would bring our complexity to log n. And internally we have to iterate over the time array, so that would be n. So n log n, and we can build the logic in this time complexity. So again, we need to apply binary search. Linear search won't work. And why we are applying binary search? Because this is a monotonically increasing function, and we need to find the minimum time. If you look over here, then there is no substantial there is no answer, and if you look at this side, then there is our answer. So binary search is going to just divide by, and it would increase our searching very fast. So that's why we are using binary search here. And let's now see how we can implement this binary search over here. If you remember binary search, we have low, we have high, and we have the mid with us. So what is mid? Mid is low plus high by 2. So in this case, it would be 0 plus 12 by 2. This would be 6. So mid would point over here. Now time, which is pointed by mid, is 6. And how many products you can make? So products made is 6. And how many products we want? We want 7 products. So it is less than this. That means in that case, you don't require this, because you can make at most 6 products at time 6. Then of course, in the less interval of time, you would make less products. So there is no point. Therefore, low will come over here. So that means in this case, mid plus 1 would be our low. Then, so what would be our new mid? So mid would be low plus high by 2. So low is pointing to 7, and so 7 plus 12 is 19, and divided by 2 would give us 9. Now our mid would point over here. This would be our mid. So mid is 9. We can make 8 products, and we want how many products? We want 7 products. So we can make 8 products, but we want 7 products. So this has exceeded. So in that case, what we need to do? That means it has exceeded. And if you want an analogy, we are searching a number, and the number has overshooted the number which we want. So what we do in that case, we bring down the high. So in that case, high would become mid minus 1. So let's do this. High would become mid minus 1. High would point over here. And now what is our mid value? So mid value is nothing but 7 plus 8 divided by 2. So in this case, this would be 7. So mid would point over 7. So again, we will check what's the value. So mid is pointing to 7, and product made is 6. It is less, so we will increase the low by mid plus 1. So our low would, which is sitting over here, will go mid plus 1. So mid plus 7 plus 1 is 8. So low will point over here. Now if you remember, our binary search go up to low is less than equal to high. So now what would be our mid in this case? So mid would be is 8. So this would be 8. So this would be 8. Now time mid is, so mid is 8. The products you can make is 7. And this is what we want. 7 is equal to 7. So time needed would be 7. And since low is now in the next iteration, also here we will make high as mid minus 1. Mid is pointing over here, not here. And this high would become mid minus 1. That means high would point over here. So high would point over here. And we have made this condition false. So our answer would be this one. I hope this is clear how the binary search is working. Simple, right? How we used to find the number, we are doing the same analogy. In case of number, we have the product made, and we are comparing with that. If it is overshooting, then we bring down the high. If it is under value, then we bring the low, and we keep on doing this. Okay, so we will have the number of machine and the products we have to make, the target product, and the next line contains a list of a time needed to make a product using each machine. So let's take n as 0, and let's make the target product as 0, and then we can get the input n and t. Then we need to create a vector of the time. This is just the time taken by individual machine. So let's get this input. So I will say while input. So while saying input, we can push back this in our time. So we have this. And also, we can reserve the space for our vector. What I've done this. Let's try to understand here. So let's say n is 3, and we have to make 7 products. Then this is going to create a vector, and we are reserving it. Just like okay, I need 3 space. So this is basically going to reserve the space. Okay. So after this, now we need to have low and high. So if you clearly see, so low would point at 0, but what should be the upper index of high? So to answer this, let's see this. So let's suppose in 1 second your machine can make 10 to the power 9 products, and in 10 to the power 9 second, how many products you can make? So you can make 10 to the power 18 products. So that means if you take the upper limits, then the upper limit of high would be 10 to the power 18. So low would be 0. Let's make it low as 0, high as 1e18. I'm taking the upper limits. Okay, so high would be present a very large number, and let's start the. So while low is equal to high, right? While low is equal to high, we should have some conditions. First is the mid value. So mid would be nothing but low plus high divided by 2. Then we need to have products made equal to 0. And then okay, so we have the mid, and now we need to create the number of products. So we need a loop to do so. So let's take ln as I is to time, and then let's simply add this in mid by I. Okay, so what I've done this. So let me explain you. So basically, we will have a vector with us. So here we have the time 3, 2, 5, and then we will iterate for each mid value product mid. So this is basically product mid is equal to. So let's say your mid is now let's say mid is 5. Let's say time mid represent time, right? So it is 5, and we divide it with the 3. Then we add 5 divided by 2, 5 divided by 5, and we will now compare. What we need to compare? If so, there would be three conditions. This condition is basically low, not low. So this condition would be if products made is greater than equal to target. That means you have overshooting the value. You are making more products. So first of all, your time needed would be that mid value, right? Because that is your one of the time. We need to define this time needed. So let's define it over here. Needed equal to 0. So that is your answer, right? Time needed. That is your answer. And also you will bring down the high with minus 1. So this is basically this condition. Time needed would be your mid value, and you will bring down the high. No, if you are making less products, your product made is less than the target value, then that means you should increase your low. And finally, we will return the time needed. So this is the little thing. And now let me write one condition which will help in preventing overshooting values. Let's say your product made exceeds at any given point of time exceeds your target value. Then there is no point of going further. So you will break, right? So this will prevent the overflow condition. So I think that's it. Let's try to submit this now. Submit. Factory machine and submit. Okay, it has been accepted. So I think this is clear what we are doing. And we first make the value as high as possible, because no matter what, it is going to be divided by 2 and it will come down. So that's not an and why we have made such a high value, because by looking over the constraint present over here. So the products made and the time. So the minimum time needed to make the products. The time needed to make a product using each machine. So let's say if your each machine takes just take how much it takes. Your each machine takes. Let's say you have 3 machines and your machines are like this. Let's say. So and you have to make, let's say 10 to the power 9 products. So your each machine takes 10 to the power 9 seconds to make one product. But you have to make how many products? 10 to the power 9 products. And your each machine takes this amount of second to make one product. So that means to make this amount of product, you would require 10 to the power 18 seconds. Hence our high value is situated at such taking these constraint condition, the high value is present at such high index. It is present at this seconds, right? Because we are giving low and high as our time, right? So 10 to the power 18, this is time, and this will be pointed by high. So that's why I am keeping this high as 10 to the power 18.